Welcome to the world of OSPF, and it is a big world. That's why we've divided up the concepts into multiple videos. In this part one, we're going to take a look at the concepts behind link state routing protocols, OSPF being the first one that we talk about, and compare them to their distance vector brothers. We'll then get into the OSPF area design and focus on what areas are, why we have these things called areas, the routers that go into them, and what are the terms used to describe them. Finally, the bulk of this video is going to be focused on how OSPF neighbors form. There's a lot to it, and that means there's a lot of troubleshooting steps that come into play when trying to figure out why neighbors aren't forming. So let's get started. OSPF is the first of the link state routing protocols that we've seen. There's only two of them, ISIS and OSPF. So before we get into the details of OSPF, let's first talk about some generalities of link state, because there's only one other category that a routing protocol can fall in, and that's distance vector. And every other routing protocol in the world is a distance vector routing protocol. RIP, EIGRP, even BGP, the routing protocol of the whole internet, is considered distance vector. So what's the big difference here? Well, link state routing protocols, first off, maintain three tables. Now you might be thinking back, if you've seen the EIGRP videos, you might be thinking, well, doesn't EIGRP do that too? Well, yes, it does, but they're kind of different. Let's talk about them. First off, link state routing protocols maintain a neighbor table. Now that is the same as EIGRP, meaning it will track all of the neighbors it has formed relationships with and are exchanging route with. So all the directly connected routers that are running the OSPF or ISIS routing protocol. The big difference of a link state routing protocol comes right here, the topology table. Every link state routing protocol will maintain a topology table, which is essentially a roadmap of every single network that is available within their area and all the possible paths to get there. For example, let's say up here I have the 172 network. That's my little arrow pointing to it. And I have all these different paths that I can use to reach that 172 network, from any point within that area. Now, every single router, we'll say this is just an area, okay, and we'll talk all about areas in just a moment. Every single router that is in that area has that same roadmap, meaning they see the whole layout. Think about, I'm sitting here in Phoenix, Arizona, right? If I wanted to get to California, you know what I'd do? I'd go to Google Maps or MapQuest, and I'd type in, what is the fastest path to California? Now, Google Maps kind of has this gigantic database, but it's thinking, oh, well, I only need to refer to the information on the west coast of the United States so that I can give Jeremy all of the best paths that he could take to get to California or to Disneyland or wherever he was going within that focus. Now, the Google Maps or MapQuest has the entire roadmap, but they will spit out only the best path to get there. That's, my list of driving directions, and that is the routing table. Now, let me not just pass up the topology table at that, because I want to make sure you see the big difference. Distance vector routing protocols, EIGRP included, may have a topology table. However, the topology table is not a roadmap of everything that's in the area. The topology table is just a list of what the neighbors have passed on. That's why distance vector is always considered routing by rumor. If I had a router here connected to all of these different neighbors, this router only knows the best of what its neighbors know. Now, EIGRP can harness that information and say, well, this neighbor has a great path, and this one has a backup path, so I'll put both of those in my topology table. But EIGRP is a far stretch away from knowing everything about the network. Maybe somewhere down the line there was another split in the network, and there was two paths to reach, this one network here. This router doesn't know about the split down here. It only knows the split of its directly connected neighbors because it is considered a routing by rumor protocol. That's the big difference, and I want to make sure I differentiate here. Link state routing protocols don't just know what their neighbors know. They know the roadmap for their entire area. And that, we'll talk a lot more about areas in the upcoming slide. That's one of the big differentiators. Now you can see as we drop down, all link state routing protocols use Dijkstra's shortest path first algorithm. This is a picture of Dijkstra, the guy who created SPF. And SPF is the algorithm that it runs that finds the best way to get to places, that takes this roadmap here in the topology table and generates the routing table. And it's funny, when I just did a search because I thought, I'd be interested to see who Dijkstra is. This guy is a genius. I mean, he was a keynote speaker. He was a lecturer, PhD in computer science. I mean, the guy is brilliant. And it was humbling just to read of some of his accomplishments, because he would go to lecture calls. And I mean, imagine being there and you're not just hearing about SPF, you're actually hearing from the guy who wrote the algorithm to run SPF. It just amazes me. But he is the guy who created that whole system. The only disadvantage of link state routing protocols when it comes to this is it can be very processor intense. I mean, compare link state routing protocols to distance vector. Distance vectors only know what the neighbors know. They only know the best of what the neighbors have told them. So when they try to figure out the best path, they don't have to sort through much, which is why the dual algorithm of VIGRP is so much more processor efficient than SPF. SPF has so much information to deal with, which is at times a benefit because it can say, well, I know the best paths of everywhere, but at times a disadvantage because they have all this information to deal with that they don't really need to worry about. For example, I mean, this neighbor down here chose the best of those two paths, right? And passed the best of those two paths up here to these neighbors. So the decision was made, why burden this router with all the processor cycles to make that decision again? That's what link state routing protocols do, is they burden these routers with a decision of an entire area. So I guess I'm stepping a little into the design strategies here. You want to make sure that your areas don't get too big. Talk more about that in a little bit. Link state routing protocols send triggered updates to announce network changes. So they don't, they're not like RIP, where they just send the whole routing table every 30 seconds or something like that to update all of the other routers. They only send an update when there's a change to the network. All the other messages, like EIGRP, are hellos. However, link state routing protocols do issue something known as a link state refresh, which after a long interval, a router that's running a link state routing protocol would send its entire routing table to say, hey, just in case you missed it, this is what I see the roadmap as. Because I want everybody to know this is what I'm seeing, just to make sure there wasn't a packet missed or something like that. In OSPF, it's once every 30 minutes. So once every 30 minutes, if no changes have happened, the routers will just say, hey, let's just make sure we're all on the same page here. Exchange, exchange, exchange. And they all check each other's map and go, yep, nope, we're good. Let's keep on routing away the same way we are. And that just makes sure that nothing gets missed. Okay, now let's focus in on terms direct to OSPF and how OSPF is properly set up. OSPF divides the network into multiple areas. And I'm kind of looking at this. This kind of looks like a Mickey Mouse network design. But every single area contains a group of routers. So let's look at the specifics about this right now. First off, all areas must connect to area 0. This will be the first area that you create every single time. Area 0 is considered the backbone area. Now, I don't want to get too deep into the specifics yet without talking about areas in general. First off, you can see all routers in an area have this same topology table. And looking at this Mickey Mouse network design, you can see that it looks very small, like there's 4 routers here, but that's just because it's a logical design. Every area has a bunch of routers. There might be 10, 50, 100, 1,000, if you wanted to be crazy, different routers inside of an area with all kinds of different networks. The point is, just like I was talking on the previous slide, all of the routers that are within the area have the same roadmap. So let's imagine that there was 50 routers in area 2. You can see that's a regular area. 50 routers would, have a roadmap of all kinds of different networks that were all connected within that area and eventually terminate to that router that's sitting on the border of that area. Every single router within area 2 would know everything about Area 2. Anytime a network went down, all the routers would know about it. Anytime a network was added, all the routers would know about it. They always have the exact roadmap of everything that's available in Area 2. Then we come to this special router sitting on the border of that roadmap. That router is known as an area border router. You can see that every single router that's connecting between two areas is a router designated as an ABR, or an area border router. And it's special in that it has one interface. I kind of think of it as like one leg in each area. I mean, here in Arizona, we kind of have a strange state. If you look at the map of the United States, you kind of have Arizona sitting right here connected to California on this side. But there's this point, and this is where you're going to find out my horrible geography, where we have, uh, there's 4 states. That's all I know. I don't know which one's which, so I'm just going to take a stab at it. Forgive me. But there's Utah, there's Colorado, and there's New Mexico. Hopefully I got those right. But we're right here in Arizona. Now there's a place where you can go, it's known as the Four Corners. You can actually drive there, and you can stand on the corner of 4 states at exactly the same time. They have this big post, kind of like this post sitting right there. It says this is the 4 corners, and if you put, you know, one hand right here, one hand right here, 1 foot, you're kind of standing like a spider. 1 foot here and 1 foot here. You are actually in 4 different states at the same time, and you get to say, "Hey, I've been to the 4 corners." I've actually never been there, but that's what the area border routers are like. It's like a router that has one interface in multiple areas. Now you can see that these routers have one interface in the backbone and one interface in area 2. But you could also have, you know, this router that maybe has another area right here that's area 3, and maybe it's got one interface connected to that, you know, kind of doing one of these 4 corners sort of effects. The point is that all areas must connect to area 0. So if you are an ABR, which these routers are, one interface can be in any area you want, or I should say multiple interfaces can be in whatever areas you want, but one must always be in area 0, the backbone. Think of it as just the design criteria that says, you know, all limbs of my network must connect to the backbone, just like the human body. Now, the point of this design is to localize the updates within an area. When you design OSPF, you want to set it up in a way that if a network goes down in area 2, maybe there's 50 routers in there. You know, all the 50 routers are going to be like, oh, network down, let's converge, let's work around, you know, where they're jumping all around, figuring out what the down network means, calculating a new route there. But the area border router should localize those changes, meaning you don't freak out the routers in area 0, you don't panic the routers in area 1. Every change is localized to that area. Now, the bigger an area grows, and when I say bigger, I mean more and more routers inside of it, the bigger the roadmap will become, and the more intense the calculations will be every single time that there's a change. Because since everybody has to have the same roadmap, anytime there's a change, every router has to know about it. That's what dictates when we divide up an area. Is really once we've reached a size that is big enough that the changes are becoming too intense. All the routers are running that SPF algorithm for a long time, every single time a change happens, because the database has become so large. Now, that's the ideal design. I've seen a lot of areas designed around geographical regions. For example, Area 0 is the corporate office in Utah. Area 1 is the branch office in New Mexico. Area 2 is a branch office in Arizona, so that when a change happens in Arizona, you don't, you know, send updates across to maybe a slow WAN link or something like that to Area 0, the corporate office in Utah. You just localize that change in Area 2. And I know I'm being kind of vague right now on localizing the updates, but as we expand more and more, you'll understand how those are localized and how ABRs really play a role. Last 2 things I'll talk about. Number 1, this design requires a hierarchical design. And any network should have a hierarchical design. But what that means is that you're designing your network in a hierarchy of IP address schemes. So Area 2 should have a design where maybe all the networks start with the number 10. You know, 10.1.0.0, 10.2.0.0. All 50 of those routers that are in that area start with 10. Then over here, you maybe have all the networks start with 172. Maybe 172.16.1.2.3, and so on and so forth. That is a hierarchical design. A non-hierarchical design means that, maybe we've got some 10 networks over here, and then I'm like, let's just throw one over there. 10.3, let's toss it in area 1 just for fun. Don't do that, because if you do, you've then started to defeat the whole purpose of areas. The purpose is to localize changes, and I'll give you a hint on how we're going to do that through summarization. If you put networks within an area that can't be summarized, for example, if we throw 10.3 over there, we can't summarize that. It's just, it's a discontiguous network. So if that goes down or an update happens, then everybody will know about it because summarization can't be applied. We'll expand more on that later. Last thing I'll talk about is the Autonomous System Boundary Router. The ASBR is the router that connects outside of your OSPF autonomous system. Let me get sloppy here. Whoosh, big circle. And I lost half an area right there. This whole circle, if it was including area 1 completely, is considered your entire autonomous system, meaning all routers under your authority. They may be in different areas, but they're all running OSPF and they're all communicating in some way. The ASBR connects you to networks outside of your own. Of course, the most common network is the internet, but it could be a RIP network, it could be EIGRP, it could be, some other domain that's running BGP, all kinds of systems outside of your own are connected through the ASBR. The reason these terms are key is because the ABR and the ASBR are the only two router types in OSPF that have the ability to do summarization, period. That's the scoop. When we were looking at EIGRP, one of the big benefits is that you can do summarization wherever you want. Any router, you just go into the interface, use that command IP summary address, and bam, you're good to go. You've got summarization happening. Not in OSPF. You've got 50 routers in area 2. The only one that can do summarization is the ABR. Can't be done anywhere else. Before we get deeper into the area design, let's talk about how OSPF neighbor relationships form. There's a little bit more to it than there was with EIGRP. First thing that I want to make sure we understand is that neighbors only form between routers in the same area. So if we were drawing a picture around this, you would see that these two routers are a sloppy picture, and we'll say area 0. So they're in the same area. We want these two to communicate and have a neighbor relationship. This is where this process comes in. First thing that happens when OSPF forms neighbors is you start the OSPF process, and the router will determine its own router ID. This is a term that you'll need to become familiar with as we start working with OSPF. The router ID is simply the router's name in the OSPF process. It's a number that the router picks for itself to identify itself to all the neighbors. So let's say this is router 1 right here. It's going to pick, it's actually an IP address, for itself and say, this is my name. So when I send a hello message over here to this neighbor, my name will be 1.1.1.1 or something like that. And this neighbor will know me as that name. Connected to another neighbor over here, that's okay. My name is 1.1.1.1. The name is just an identifier for the router. Now we're going to see as we get into the advanced configurations of OSPF that you really need to know the names of your router. There's some configuration that you'll be typing in that tie directly to the names. So before we get any deeper on that, what you'll need to see here is that the name will be, the router ID will be, the highest active IP address when OSPF starts, where loopbacks will beat physical interfaces. So here's a router down here that has 3 interfaces, a WAN link and 2 LAN connections, 10.1.1.1, 192.168.1.1, and 172.30.1.1. Now, which one becomes the router ID? Well, that's pretty simple. The highest active IP address is 192.168.1.1. So when we start the OSPF process, it will look at the interfaces and say, that is my name. So from there on out, when it speaks to other routers, that will be its identifier that it uses. Now notice in parentheses, I have loopbacks beat physical interfaces. So let me draw a loopback interface on here. That's how I always draw them. And I'll give it, 1.2.3.4 is its IP address. The lowest IP address of the whole bunch But you know what? Since it's a loopback, that automatically wins. So it says, okay, out of all these, oh, loopback is the highest IP address. So that will become my router ID. Now, if I add a second loopback and give it 2.3.4.5 as its IP, that becomes the router ID because it is now the highest loopback IP address that is on the router. Now, I'm going through all this trouble to explain the process to you because there are hard-coded configurations that I'll be typing in, let's say on this router that says, when communicating with this router ID, I'll be typing that in into the syntax, do these things, and we'll see those configs in a little while. So if it is the highest IP address and loopbacks beat the physical interface, that means that it can change. Let's say down the road, I add another WIC card and give it 200.1.1.1. Or I just add a loopback interface for some testing purposes. Poof, the router ID changes, the name of this router changes, and all my hard-coded config that I type in on that router up there breaks because the router ID changed. So it's very dangerous to have a changing router ID. Let's throw one more thing on this explanation. The OSPF router ID only changes when either the OSPF process is restarted or you reboot the router, which I guess is the same thing. So here's the nightmare. You go in and you're doing some testing purposes one day, it's September 1st, and you go in there and add a loopback to do some testing, and you leave the loopback on there. Now, the router ID doesn't, poof, change automatically. It waits till either the router reboots or you clear the OSPF process, you reset the process, and then it says, oh, I've got a new router ID. So now the question is, how often does Cisco routers reboot? Not often. I'm now in production. I'm not talking a lab environment here. They actually had a Packet magazine that was published where people were submitting their longest uptimes, looking at the show version. And the one that won, guess how long it was up? 8 years. The Cisco router had not rebooted for 8 years. So here's the scoop. You add that loopback interface. 8 years later, your router reboots, hopefully because you're upgrading it. But 8 years later, the router reboots, and it comes back up, and the router ID has changed, and OSPF now fails between these two routers. Now, are you going to remember 8 years ago you added this loopback interface? No way. I can't even remember what I did yesterday. So this neighbor relationship thing has to be, a little more solid than just allowing these IP addresses to be chosen dynamically. And that is why Cisco recommends to hard code the router ID using the router ID command. We'll talk about the hard coding when we get into the configuration, but by typing it in there, you overrule everything. I mean, if we had a little hierarchy, an organizational chart, you'd have physical interfaces, above that would be loopback interfaces, and above that would be the router ID command, which never gets beat by a physical interface. That's the first step. The router figures out its name using one of those three methods. Second step, the router then adds interfaces to the link state database dictated by the network command. Just like we saw with EIGRP, we're going to go into the routing process, router OSPF, and then we're going to type in network and what networks we want to run OSPF for. And that will dictate which interfaces will be included in the OSPF process and which interfaces it will decide to send hello messages on to find other OSPF neighbors. So once it adds those interfaces to the link state database, to its roadmap of the network, it will then send a hello message on the chosen interface or interfaces, depending on what you've dictated with the network command. This is considered a down state, meaning the router has sent a hello message out on its interface, but is still waiting to hear back. You'll see the network is right now considered down because we haven't formed any neighbors on there, or I should say the neighbors are considered down because no neighbor relationships have been born. Now let's talk a little bit more about the hello message. Hello messages are sent once every 10 seconds on broadcast or point-to-point networks, once every 30 seconds on non-broadcast multi-access networks like frame relay, ATM, those kinds of networks. And we'll talk more about that. That is how often those hello messages are sent. It is tunable. I can tune it lower or higher depending on how much bandwidth I want to eat up with hello messages versus how fast I want to converge if a router is considered down. Now, with that statement, keep in mind that the dead timer is once, or I should say, is 4 times the hello timer. So for instance, on a broadcast or point-to-point network, it's going to send 4 hello messages before it considers that neighbor down. Or right here, 4 hello messages on NBMA before it says, oh, you're no longer responding because you haven't responded to my hellos. That's pretty out there, meaning think about this. 4 times 130, that's 120. 120 seconds, 2 minutes before you would even realize that a neighbor is down. Keep that in mind because that should be a warning to you that a lot of the default timers of OSPF need to be tuned in order for it to be more efficient. Now, let's focus deeper into the hello message. The hello message, I compare it to an envelope. That's why you see this envelope on here, which a router receives and opens up. It looks inside of that hello message and says, oh, well, here's all the information about that neighbor. A hello message is more of like a profile, if you will. When this router right here sends a hello message, it's essentially sending this profile over to the other router. I guess a rough analogy would be kind of like the what is it? This is going to be horrible. Oh, eHarmony.com. I hear it on the radio all the time. The online dating service where you send hello messages that are essentially your profile, and you're saying, "Hi, I am this person. You know, here are my criteria. This is my name. This is how often I'll say hello, and I'll be dead." You know, I guess that's where the online dating breaks down, right? But it's not just a hello like, "Hi, here I am." It's a hello that has a lot of information about that individual neighbor. So inside of a hello packet, it will have its name. It will have how often it says hello and how long it will be until it considers someone dead. Now notice that some of these have little asterisks behind it. OSPF is very picky about neighbors that it will form. Anything that you see an asterisk behind means that the neighbors have to have these things equal in order to become neighbors. So obviously they don't have to have the same name. You can't have the same name. You have to have unique names. But their hello and dead timers must be the same. Otherwise, a neighbor relationship will not form between those two. They have to have the same network mask, meaning the IP address and subnet mask that's assigned to that interface has to be the same subnet mask that's assigned to that interface. So if you're using a /24 on that interface and, you know, I don't know, a weird network config, you mistakenly put a /30 over here, well, then the neighbors won't form because they don't have the same network mask. They have to be in the same area, meaning this interface has to say, hello, I'm area 1, and you have to be in area 1 or else we won't speak. The neighbors is the list of neighbors. And you know what? That has a star after it. That shouldn't have a star. Hang on one second. Poof, gone. The neighbors is a list of what other neighbors this router has. So for instance, if router 1 sitting up here is connected here, it might send a hello packet and say, hi, this is who I am, but I know about some other people too. Maybe I've got a neighbor over here that I've formed, and let me tell you about who they are. So that helps in determining what neighbors router 1 has, and you're going to see that helps in determining if this is a new relationship or this is an old relationship. For example, hello packets are sent once every 10 seconds. So you'd figure after, 30 seconds, you're going to get hello packets that have a lot of the same things. So if router 2 in this picture gets a hello packet and sees itself in the neighbor table, meaning it sees that router 1 already knows, oops, I put router 1 over there. Sorry, router 2. If router 2 sees that router 1 already knows about him, meaning router 2 sees itself in router 1's neighbor table, then it's going to say, oh, this isn't a new relationship. This is just another hello packet, that was sent 10 seconds ago, and I'm assuming I'll get another hello packet 10 seconds from now, and I'll also be listed as a neighbor because we formed an existing relationship. If it doesn't see itself in that neighbor table, then it's going to say, oh, it's a new neighbor. I don't know about this person, or they don't know about me, so let me give them more information. Now, router priority and the DR and BDR, I'm going to talk about later. Just trust me on that one, because that deserves a full explanation. But the last one that you see in the list is the authentication password. If you want, just like an EIGRP, you can password protect your routing domain. You don't want just any router out of the woodwork to jump into OSPF and say, "Hi, I want to be your neighbor. Here's some information." Because that could be an intruder trying to poison your routing table or get information about your network via a sniffer. So a password will say, you have to have the same password in order to become a neighbor. Notice the asterisks. Keep those asterisks in mind, because if one of those are off, the neighbors will not form. So router 1 sends that hello packet containing all that information to router 2. Step 4. Router 2 receives the hello, and if you're doing debugs or show IP/OSPF neighbor commands, you will see that router 2 immediately enters an init state with router 1. It will now list router 1 by its router ID. It will say, hey, I found a router, this is its name, and I am currently in the init state. And I'm going to keep flashing these states up as we go, because it's one of your major troubleshooting tools. First, it starts with down, when it hasn't received any hellos. Init means I've received a hello, but it doesn't mean that we've formed a neighbor yet, because after it receives a hello, it has to check. Do I have the same hello and dead interval as you? Do I have the same network mask on my interface? Are we in the same area? Do we have the same passwords? Because if any of those are off, I can't be your neighbor. And I'm going to cycle you back to down, and you'll actually see in your show commands the neighbor go from init to down. Init to down, down to init. It keeps flashing back and forth as it receives those hello packets and analyzes it. Bing, key point to you is to say, okay, if it's cycling between init and down, I better check one of those first 4 criteria here, or these 4 criteria, to see if any disagreement is happening between these two routers. 99% of the time, that'll be it. But let's say it checks all these things and router 2 is like, hey, that's good. We look good. Let me send a reply hello to you. When it does that, once it checks out and all those criteria are good, it enters the two-way state. And you'll see that in your neighbor fields. The neighbor is considered a two-way neighbor, and that's the point where router 1 and router 2 both look at each other's hello packets and says, am I already listed as a neighbor in your hello packet? One of those fields that was in the hello packet was the list of neighbors. If I am already a neighbor, then this is just another one of those hellos, just like I was mentioning before. Just another hello. They come once every 10 seconds, so I should be used to them by now. I'll just reset the dead timer, which by default is 4 times that update timer. And it's going to say, okay, you've sent a hello. I now am going to wait another 20 seconds before I consider you dead. 40 seconds before I consider you dead. 10 seconds later, get another one. Okay, another hello. Let's reset the dead timer. If I'm not listed as a new neighbor, then this is a new neighbor relationship. That's fantastic. I've found a new bud that I can exchange routing information with. Let's go ahead and continue on this process. Now, let me make a note here. If they are already neighbors, step 5 is where the neighbor relationship ends. Meaning they already know about everything because they've formed a full neighbor relationship. So there's no need to exchange routing information. If they're new neighbors, that's where we move on to step 6. So let's say that router 1 and router 2 are new neighbors. Let's follow the process. Step 6 is where the master-slave relationship is determined. And when they make it this far, they enter the X start state. That actually stands for exchange start. That means the hello packets agree that they think, you know what, the hellos turn out good, so that means we can be neighbors. Let's start the exchange of our link state databases. Let's give each other all the information that we have about the network. Now, the master-slave relationship isn't that big a deal. I've explained this to some people, and they just, oh, this master-slave thing is like the end of the world. But it's not that big a deal, because all it determines is who sends the information first. Whoever is the master, like let's say router 1 becomes the master and router 2 becomes the slave, that just means router 1 will send its link state database to router 2 first. And router 2 will look at it and say, oh, this is interesting. The slave will send it second. So that's all the master-slave relationship really determines. But let's talk a little more in depth about how one becomes the master. The master is determined by something known as the router priority. Now that's one of the hello fields that I said we're going to talk about later. Right now, we're just going to say that all the priorities are set to 1, which is the default. So by default, all the priorities tie unless you get involved and try and break that tie. So the router ID breaks the tie. Now, this is one to remember because the higher, keep in mind, the higher router ID wins, which for most things with Cisco, lower is better. In this case, whoever has the higher name, the higher IP address, breaks the tie and becomes the master. Now, the master will send a database description packet. And the way I describe a DBD, that's database description packet, is it's like Cliff Notes of the linked state database. If you've ever gone to school for any length of time, you know that Cliff Notes are your friend. Anytime you have to do a big report on a book or some novel of some sort, Cliff Notes are like the summary of the book. So rather than read the 1,100-page book cover to cover, you grab the Cliff Notes and it's like, oh yeah, you know, Homer did this to the Iliad and you know all of this information. Obviously, it's been a while since I've read Cliff Notes, but it's just a summary. Meaning, why on earth would router 1 send the whole roadmap to router 2 when there's a chance that router 2 already knows most of the things on that roadmap? For example, maybe router 2 formed a relationship with router 3 out here somewhere in the blue, and router 3 sent its whole roadmap, which is the same thing because they're all in the same area. So router 2 pretty much has nearly the entire roadmap until it communicates to router 1. So why send the whole roadmap all over again, eat up all that bandwidth, when router 2 is just going to look at it and go, oh, I've already got most of that stuff. I know about that. So a DBD is just the Cliff Note version saying router 1's like, hey, here's the summary I know about this network, this network, this network, this, you know, just kind of a list of all the networks it knows about. And router 2 gets the summary and looks at it. It's like, okay, got it. You know, it's kind of looking down that summary list of all those networks. Got that one, got that one, got that one, got that. Oh, here's a new one. You know, I didn't know about that network, which maybe was a network attached to router 1 over here. That's really all the DBD does, is allow router 2 to have an idea of what networks it knows about from router 1's and which ones it doesn't know about. Meanwhile, you can see the master sends it first. The slave also sends a database description packet to the master, saying here's all the networks that I know about. So both of them are going to acknowledge that they received it because OSPF is reliable. They both send a little acknowledgement message saying, okay, I got the description, and then they start analyzing it, looking down the list. The master's looking at the slave going, okay, got that. You know, it's kind of like going down the checklist. Got it. So each one is acknowledged and reviewed. While they're being acknowledged and reviewed, you will see their states change to the loading state, meaning they're no longer focused on exchanging the information, which was that X start state up here at step 6. They're now loading the information into memory and seeing which ones they need. During the loading state, a very, well, I won't say sophisticated, but a very in-depth process takes place where the slave and the master are going to go down that list and start requesting the details, beginning with the slave. The slave received the DBD packet first. It received that from router 1 over there. So it's only natural that it's going to go down that list and say, okay, well, I need to know about this and I need to know about that. And those are known as LSRs, link state requests. So I don't know why I cleared off all my notes there, but router 2 is looking down that list and it goes, okay, got that. Oh, didn't know about that one. There's a network I don't know about. So it sends an LSR saying, yeah, you know, at the bottom of your Cliff Notes, there was that 172.30 network. I didn't know about it. Give me all the details. So the master over here responds and says, oh, well, here's all the details. That's known as a link state update. Here's the next hop address that I'm using. Here's the cost to reach that route, meaning the metric to get there. You know, here's all the info about that route so that you can complete your database. You can have a full picture of what this network looks like. So the slave is going through that list, sending one LSR, one link state request for every network it doesn't know about. Maybe it was 2 networks it didn't know about. 2 LSRs will go out, and the master will respond with that LSU saying, here's the information. Now, once the slave has finished requesting all of its information, the master then says, oh, slave, slave. What, I don't know about this network over here. I looked at your list that you gave me, your Cliff Note version, and there was one network on there that I didn't know about. Give me the information. So the slave will respond just like the master did and said, here's the information about those networks. That LSR and LSU process continues until the neighbors are synchronized, meaning the master has requested everything from the slave has requested everything from the master. They now have the same link state database. That's when you will see the neighbors at a full state. And that's when bells ring and we go, yay, the neighbors have formed. That's the good state that we want to see when we do a show OSPF neighbor command, because that will display all the neighbors and we should see them all as full. If they get stuck in any other state, like the init or the xstart or something along those lines, that means something has failed in the process and we've got to start looking back and trying to figure out what's going on with those neighbors. That is just the neighbor process to bring neighbor relationship up. Now, the databases have synchronized and we can run Dijkstra's SPF algorithm to figure out what to do with all of that data. The routers all have the roadmap. They're all looking at the same page now. Now they've got to generate the routing table from that. But that's where I'm going to draw the line here. I don't want this video to be too overwhelming with all of this information. I just wanted to focus on the neighbor relationship. We'll talk about the Dijkstra algorithm and generating the routing table in the upcoming video as we look at more of these concepts. But aren't you amazed at EIGRP compared to OSPF? I mean, think back. If you saw the EIGRP videos, think back to that neighbor process. Hello, packet. Hi, George. Hi, Fred. No router ID to worry about, nothing like that. Hey, what's your K values? Oh, I've got these K values. Okay, let's be neighbors. I mean, that's all there was to EIGRP. If the K values were different, nah, that's the only showstopper there. Other than that, the neighbor relationships just happen and then the update packets are sent. So with OSPF, it gets so much more complex, which is why there's such a huge knowledge curve when a business goes in to run OSPF, because there's so much more that you need to know to make OSPF work efficiently. So let's wrap things up and hit the high points. We have taken a look at, first off, the link state routing protocol concepts, OSPF being the first link state protocol that we spoke about, and talked about the difference between that and distance vector. We then got into the area design and terminology, seeing the reasons to design areas to keep that roadmap smaller, to keep the link state database manageable, and also to implement summarization to make your routers more efficient. And then the terminology, things like ABRs, ASBRs, talking about where those fit into the grand scheme of things. But by far, the biggest focus of this entire video has been the neighbor relationships, understanding how those form, because that is a huge troubleshooting step. I hope this has been informative for you, and I'd like to thank you for viewing.